So the first one, most of you did pretty good if you knew where to start. If you like didn't catch where to start, or didn't catch that it said factoring, obviously it was hard to move forward, but it said to factor here. So I really just wanted to find a way to factor. When you look at these, there's two different trig functions. Can't factor with the two different trig functions. It's like having an x squared and a y. But your secant and your tangent have a relationship that is linked with the Pythagorean identities. Tan squared plus 1 equals secant squared. So I can replace secant squared with tan squared plus 1. And then I would combine my like terms from there. I'd get tan squared x plus 4 tan x plus 3. And then if you want to keep the tan, you certainly can, but you could also replace it. I could say like a equals the tangent of x, and I'd get a squared plus 4a plus 3. And then factor that. The factors of positive 3 that sum to 4 are positive 1 and positive 3. And then you just can't forget to bring that tangent back in. So it should have been tan of x plus 1, tan of x plus 3. Order doesn't matter there. They just both needed to be there. Don't forget to bring the tangent back in. Overall, pretty good. Again, if you like forgot and didn't know how to start, obviously it was a little bit rough. But other than that, if you did start, most of you got to the right answer. The second one, and this to me is like super obvious. Anytime you've got a pi over 2 minus an angle, go to your cofunctions. On your cofunctions list, cotangent is linked to tangent. So this is the same thing as saying the tangent of theta over the secant of theta. I lost the C. You could rewrite that as like sine over cosine over 1 over cosine. And then flip that, and I get cosine over 1. The cosines cancel, and I just get sine of theta. You can also take the secant and move it to the top as its reciprocal function. So this could also come up as cosine, and then I would have changed tangent to sine over cosine, and then the cosines canceled out. So you could do it either way. Questions on that one? Yeah.
What happens to the cosine on the bottom?
So in the second, like in the way I did it the first way, this one, this gets over here. I flipped it. So I did times cosine over 1, and so I brought it to the top.
Oh, okay.
All right, then 3 look like this. All right, for this one, and there's a couple different ways to start it. If you started on the right, that's 1, and you would have gotten stuck. Like secant squared minus tangent squared is 1. On the left, if I give them a like denominator, well, there's two ways to do it. One is bring the denominators to the top as their reciprocal functions. So as secant goes to the top, it would become cosine, and this would be cosine squared theta. On the right, cosecant can come to the top as its reciprocal function, which would be sine, and I'd get sine squared theta. And then cosine squared plus sine squared is 1. So either way, like if you start on the left, you get stuck at 1. If you start on the right, you get stuck at 1. Which means you kind of had to work both sides on this one, which is okay. Usually you want to stick to just one side, but if you get to 1 and you're stuck, you can keep going on the other side. Okay, this is, yeah. All right, this one, on the left-hand side, you've got a perfect, or difference two squares. And on the right-hand side, you don't. So I would say I would try, and the left-hand side has two different trig functions. I would say I would try there first. So if I factor this, this would be sine squared theta plus cosine squared theta. And then sine squared theta minus cosine squared theta. So that's the difference of two squares. They're both perfect square. There's a minus between them. Sine squared plus cosine squared, this whole thing here is 1. So I got rid of that first one, but the second one's still there. And on the right-hand side, there's only sine. I would go to my Pythagorean identities and I would see, is there a way to replace cosine squared with something related to sine squared? And because sine squared plus cosine squared equals 1, if I want to replace cosine squared I'd have to move sine to the other side. So cosine squared would equal 1 minus cosine, or sorry, 1 minus sine squared. So then this sine squared stays as sine squared, minus cosine in here is going to get replaced with 1 minus sine squared. That negative goes to both. So I get sine squared theta minus 1 plus sine squared theta. And sine squared plus sine squared would be 2 sine squared theta minus 1. And now the left side equals the right. Questions on that one? All right, with this one, and a lot of you maybe even had a hard time starting it. If you use the right side, I came off the TV, that's helpful. If you factor the sign out on the right-hand side, wait for it. Let's say I take a sine squared out here, right? I end up with 2 minus sine squared theta. And then I want to rewrite this in terms of cosines because on the left, they're cosines, right? So if sine squared plus cosine squared equals 1, then sine squared, if I move this over here, would be 1 minus cosine squared. And 2 minus sine squared theta, the sine squared can be written again as 1 minus cosine squared theta. I'd have to distribute the 1, or the negative, 1 minus cosine squared theta, 2 minus 1 plus cosine squared theta. And I get 1 minus cosine squared and 1 plus cosine squared. That one's a little weird just because we haven't done really anything like that. But sometimes you got to think outside the box. Like, remember to always check for factoring, especially if the left side and the right side are two completely different trig functions. You got to figure out how to write one in terms of the other. All right, this is, I don't even know what number we're on anymore, 6? Tan squared sine squared equals tan squared theta plus cosine squared theta minus 1. So because the left is tan and sine and the right has tan and cosine, I would try to see again if I could try to get the right side to either be the sine or the left side to be the cosine. Cosine squared minus 1 is what? It would be if sine squared plus cosine squared equals 1. You could do two things. Just replace cosine by itself, right? Or if I subtract this, I can move sine to the other side. It would equal negative sine squared. So I could get tan squared theta minus sine squared theta by replacing cosine squared minus 1. If you only replaced cosine squared, it would have been tan squared theta plus 1 minus sine squared theta minus 1. So it would have been one more step, but eventually you get rid of that minus 1 anyways. Now on the left-hand side is a product, on the right-hand side is a difference. So I would make this sine squared over cosine squared minus sine squared. And then in order to get them to one fraction, I'd have to multiply both the top and the bottom by cosine squared. I'd get sine squared minus sine squared cosine squared over cosine squared. I can take out the sine squared, so factoring again here, 1 minus cosine squared. One minus cosine squared is sine squared. So I can get sine squared times sine squared over cosine squared. And remember, if they're all being multiplied, or if it's the product in the top or the bottom, I can actually just split that And then it looks, well, I'll split it the other way. Split it this way. And then it looks like the left. Sine squared over cosine squared is tan squared times sine squared. God bless you. You're welcome.
Miss,
Yeah.
how did that become 1 minus cosine squared from sine?
Because sine squared is 1 minus cosine squared. Sine squared plus cosine squared is 1. Right? Sine squared plus cosine squared. It all goes back. It keeps going back to Pythagorean. So sine squared itself would be replaced by, or 1 minus cosine squared could get replaced.
And where did the cosine squared go? Like that was next to the sine squared. Is it like disappeared?
This one,
Yeah.
I factored out the sine. So then it's 1 minus cosine squared.
Wait, what do you mean factored out?
There's a sine here and a sine here. So I took it out.